Hello again, pre-calculus students. In this lesson, we're going to study multivariable linear systems. Multivariable means they're going to have more than just x's and y's, and linear systems means that they're all going to be, x to the first, y to the first, and z to the first power. So if you have a system with three linear variables in it, it's a plane. 2x plus 5y plus 4z equals 30 is a plane. But just x plus 3x minus 7y equals 2, that's a line. So 2 variables gives us a line, 3 variables gives us a plane. Let's take a look on page 491 of our text, what answers might look like. So if we're doing a systems of equations in 3 variables, we're talking about planes. So in this one, your 3 planes intersect at one point and there is a solution x, y, z to your system of equations. So this would be a consistent and independent system. It has exactly one solution. This one would be consistent and dependent because every point on that line, that black line there, satisfies all 3 equations that make those planes. So there are an infinite number of solutions on that line of intersection. Now, what if all 3 of your equations turn out to graph the same plane? Well, that's another infinite number of data points. So that would again be consistent and dependent. Here it's possible for your 3 planes, there's nowhere anywhere where all 3 planes meet at the same point. So this would be an inconsistent system. There's no solution. And here we have 3 parallel planes, they're not going to meet. So again, that's inconsistent. I'm going to teach you a method for solving systems like this. I know in the past in algebra classes you have learned, hey, just try to eliminate variables, eliminate one variable 2 different ways. We're going to come up with a system, an algorithm, a step-by-step process to solve these problems, because then that process will lead directly to matrix operations, and then it's easy to have a computer do it, as long as you do it with this step-by-step algorithm. And this algorithm is called Gaussian Elimination. It's named after a guy named Gauss, Carl Friedrich Gauss. So this is a checkpoint problem on page 490 of our current textbook. And here's our system of equations. You can see I've got 3 equations and 3 unknowns. What I want to do is manipulate these equations. So the first equation still has all 3 variables. The second equation, I've eliminated the first variable x. And in the third equation, I've eliminated the x and the y. So you can see I can get z equals something. Then I can do what's called back substitution. I can take that z, stick it in here, solve for y. Then I can back substitute the z and the y into here and solve for x. When you get it in this format, it's called echelon form or row echelon form. Here are the 3 rules. These are the only things you can do to your equations. These are the rules of Gaussian elimination. You must memorize them. Not necessarily word for word, but you must know what they mean, understand what they're doing, and be able to go, oh yeah, I can only do these 3 things. 1, you can interchange 2 rows. In other words, if I wanted this row to be first and this row to be second, I could swap those 2 rows. Obviously, it doesn't matter if I'm, which order I write the equations in. Second, you can multiply one equation by a non-zero constant. In other words, I'm going to take one equation and multiply it by 5. And then a third step is you can take a multiple of one equation, add it to a second equation, and replace that second equation with the new sum. And I'm sure you're going, ah, not to worry. It'll make sense to you in a few minutes. So make sure you have this written down. Pause now because I'm moving on. Here's how we solve that system of equations. Now, I said that you can use, one of the operations was take a multiple of one row, add it to a second row, and replace that second row with the new sum. So here's my system of equations. You always draw an arrow from here to here. So this arrow says I'm taking the second row and I'm replacing it. And what am I replacing this row with? I'm replacing it with a multiple of the first row plus the second row. Now the catch is, if you read that rule, go back and read your rule correctly, there's no way you're not allowed to go -2 row 1 plus 3 row 2. It doesn't say you can take a multiple of one row and add it to a multiple of the second row. The rule only says you take a multiple of one row and add it to a second row. Now, if you multiplied it by a multiple of the second row, yeah, I'd ding you for that. But it won't make your answer turn out incorrect. What doing that does, though, is that screws up operations in matrix algebra when you get to linear algebra. So I want to get you doing this right from the beginning. And why did I do this? Well, the first thing we always want to do in Gaussian elimination is we'd like to have a 1 or a -1 up here in this corner, because I want to get rid of these two variables down here. And you'll notice I want to do that because we go back to my echelon form. I want to have something up here and nothing below it. So I want to get rid of these two. So if I have a 1 or a -1, that's really easy to get rid of these. So if I multiply the first row by -2 and add it to this row, so -2 row 1 plus row 2, you see that I got rid of that x value. So -2 times 1 is -2 plus 2 is 0. Now I go my y's. -2 times that 1 is -2 plus that -1 gives me a -3. So there's my -3y. -2 times 1 is -2 plus 1 is -1. And then -2 times 6 is -12 plus 3 is -9. And then I did the same thing here, but I took -3 times row 1 and multiplied it by row 3. Don't play games. Don't go, ooh, I know what I can do. I can eliminate these y's by adding row 2 and row 3. Follow the algorithm. The algorithm says eliminate these two, then eliminate this one, then solve for z. So by doing these two row operations, I've gotten rid of these two x coefficients. So by drawing an arrow here, I'm saying I'm replacing row 3 with -3 times row 1 plus this row 3. Your second term in these linear combinations will always be plus whatever row you're replacing. I'm replacing row 3 here, so I'm going to be adding -3 row 1 to row 3. All right. Now I say I want to interchange two rows. So I moved this row from the third row to the second, and this one from the second row down to the third. Why did I do that? Because I noticed, ooh, I can divide everything by -2 here, and I can get a 1y. So I swapped those two rows. Now I'm going to replace row 2 with -1/2 row 2. So -1/2 of this is +1y, -1/2 of this is +2z, -1/2 of this is +8. And then my third row stayed the same. Now I used this one up here to get rid of what was below it. Now I'm going to use this one right here. Don't use this one because that would introduce an X again. Now we're going to use this one to get rid of this term by going 3 row 2, so that'd give me a 3y plus row 3. 3y plus negative 3y, there's no y term. Now I'm in echelon form. I have 3 variables here, 2 here, 1 here. And I can substitute. First, I get z equals 3. Now if z equals 3, y plus 6 is 8, y is 2. Well, if y is 2 and z is 3, what plus 2 plus 3 equals 6? 1. And then you take these 3 numbers and you substitute them into the original equation. 1 plus 2 plus 3 is 6. 2 minus 2 is 0, plus 3 is 3. Okay, that one checks. And 3 plus 2 is 5, minus 3 is 2. So this x equals 1, y equals 2, z equals 3 satisfies all 3 of these equations. It's a check. Here is page 497, number 28 in your book. You'll notice the first thing I did is I swapped row 1 and row 3. That got me a 1 up here. I also liked it because it had 1s up here that I can, that'll be easier to deal with later. Then, all I have to do is do negative row 1 plus row 2. Don't write it row 2 minus row 1. That's not what our rule says. Our rule says you can take a multiple of one row and add it to a second row and replace that second row with this new sum. So negative row 1 plus row 2, that got rid of this x, and negative 2 row 1 plus row 3 got rid of this x term. Now I've got a negative 3 here and a 2 here. I'm just going to multiply this row by 2 and this row by 3. That way I get a negative 6y and a 6y. Remember, one of my rules says you can multiply a row by a non-zero constant. Well, I multiplied this row by 2. I multiplied this row by 3. Now I could just add rows 2 and 3 together and replace row 3 with the sum. Please substitute these 3 numbers into all 3 of these equations to make sure that they check. Here's page 497 of our current book, number 29. I had a 1 here, so I'm going to interchange these 2 rows. That's what these arrows mean. So I can get the 1 here. That gives me the very easy row operations. But now look what happens. After I've gotten rid of the x and y, gotten rid of the x terms, I have 5y minus 5z equals 25 here, and I have 5y minus 5z equals 32. How can both of those be true? Because they're both 5y minus 5z. This isn't going to work, folks. This one has no solution. If you had gone one more step, you'd get you'd go negative row 2 plus row 3. You'd get a 0, so you'd get 0z equals 7. Well, how can 0 times z equal 7? Again, no solution. Here's page 497, number 37. I could have swapped these 2 rows. I just wanted to show you you don't have to. I noticed all 3 of these were divisible by 3, so I did that, multiplied by 1/3 to get a 1 there. So I did a negative row 1 plus row 2 to get rid of this x term. I did a negative 5 row 1 plus row 3 to get rid of this x term. Here's my new system. Now I notice I use this one to get rid of this one. Hey, and I don't have to multiply by constants like I did last time. I just do row 2 plus row 3. Uh-oh, 0 always equals 0. So I have 2 equations and 3 unknowns. This is going to be where 2 planes are intersecting. So this one, because 0 always equals 0, this one's going to have infinitely many solutions. What will those solutions look like? Well, don't panic about this. I'm not going to give you this on a, I don't think I'm giving you one like this on a test where you have to give your answers this way. But anyway, here's what we started with on the last page. I want to multiply by 1/3. Alrighty, so let's start with z. I'm going to let z equal some constant a. You let z be a be anything. So y minus a equals 1. So I'm going to add both sides. Y equals a plus 1. And then x minus a plus 1 plus 2a equals 2. You can solve that and you get x equals negative a plus 3. So you pick a value of a, and here's a solution to that original system of equations. I said it had an infinite number of solutions. Well, there are an infinite number of values you could pick for a, and as long as they're of this form, that will be a solution to the original system of equations. Again, I don't think I'm going to give you a problem like this on a test or a quiz, but showing you now how to do it. And if I do give you one, well, obviously we'll have more practice later. There are non-square systems on page 493. A non-square system is one where you don't have an equal number of equations and unknowns. This is a non-square system. It has 3 equations and 2 unknowns. So that's, you can take a look at those on page 493. Now I want to give you a preview of what's coming up. How can we use this? Well, perhaps you know that through any 3 points, through any 3 non-collinear points, you can always draw a parabola. Or through any 3 non-collinear points, you can always draw a circle. And look, I think I did a pretty good job here of saying this point, this point, this point, kind of sort of trying to eyeball the center and then draw the circle. I think I did a pretty good job. So what is the equation of the circle that goes through here? And what is the equation of the parabola that goes through here? We're going to use systems of equations to solve that. And the way we're going to do it is we're going to make use of this equation, which is good for all conics. And remember that a parabola and a circle are a conic section, as are ellipses and hyperbolas. Those are our 4 conics. So a couple things to remember about that. You know what? I'll write Leah T anyway. So here's the equation of a circle where h, k, and r are all constants. If you FOIL this out, don't forget that 2hk term or negative 2hk term in the middle. And then if you FOIL this out, don't forget your negative 2ky term in the middle. Then what I did is I grouped these together. So I have x squared plus y squared plus there's my negative 2hx. There's my negative 2ky, and then these are all constants. If I group those together, that's where I get a 1x squared, a 1y squared, a dx, an ey, and an f equals 0. That's where this came from. I'll be able to use that. So let's just start with a circle centered at the point 3, 4 with a radius of root 10. So if I FOIL this out, I get this. Don't forget that negative 2hx, negative 2 times 3 times x. Don't forget your negative 4y, or your negative 4 times 2 times y here. And then when we group it all together, we get this equation. So this is my x squared plus y squared minus, or plus dx, where d is -6, plus ey, where e is now -8, and then plus 15, that's f, equals 0. So to get back to, from this form back to this form, we complete the square. X squared minus 6x, y squared minus 8y, bring the 15 to the other side. To complete the square, I take half of -6, which is -3, and square it. I add 9 to this side, I add 9 to this side. Keep it in balance. Take half of -8, that's -4. I square it and get 16. I add 16 to this side, I add 16 to this side, and you can see that we're right back to where we started. So you should be able to go from here to here, back to here with your previous algebra knowledge. And if you can do that, you're going to have great fun. It'll be easy peasy to solve those equations. What's the circle through the 3 points, and what's the parabola through the 3 points? So that's what's coming up. I know that was a lot of information and a lot of writing, but you're going to get good at this. This is a fun chapter. Don't worry about it. We'll get you through. Anyway, have a great day.